It is a little known fact that 0.999999999999999 is equal to 1.000000000. But like, why though? I mean, sure, they're pretty damn close, but like, are they actually the same number? Is there an actual reason to it? Well, the first reason, which you may have seen, involves letting 0.9999999, which we'll just call 0.9 recurring, be x. Just call it x, and then what's 10x? Well, infinite number of 9s, so it's just 9.99999999999.9 recurring. That's something that we apparently are allowed to do. So just subtract x from 10x, and we have 9x equals 9.9 recurring minus 0.9 recurring. The 9 recurrings vanish, and we're just left with 9x equals 9, which means that x is 1. So, is that it? Have we solved the problem? Can the video end now? Well, I'd say not quite. See, the thing we're dealing with here is decimal expansion. Now, the thing to remember about decimal expansion is it's a human invention used to describe numbers which aren't whole and maybe even aren't rational. And so for some random number between 0 and 1, we can write 0, decimal point, and then a string of digits, however long we need. They could go off to infinity. That's what a ... generally indicates. And each digit with its place value tells you what we need to add to our running total to get up to the real number we're describing. So in pi minus 3, the 1 tells us we need to add 1/10, and then 4/100ths, and then 1,000th, 5 10,000ths, and so on, and we keep working our way up closer and closer to the real number, which in this case is pi minus 3. But you probably know this, so why am I explaining it? Well, I want to stress that this is a way of representing numbers which would exist even if we used a different system to represent them. And the real number we're describing is the limit of its decimal expansion. It's the limit as you keep adding on the millionths and billionths and quadrillionths given to you by the decimal expansion. And this is the same for 0.9999999 ... only this limit is a little more subversive. And of course we show through algebraic manipulation that the limit of 0.9 recurring is 1. But algebraic manipulation is something you should be careful about, because sure, you know, x is this 0.9 plus 0.09 plus 0.009 plus ... But let's say we had y be a different infinite sum, 1 minus 1 plus 1 minus 1 plus ... We just keep alternating with a positive and a negative 1 being added to the sum. And we can actually manipulate this sum to show that 1 minus y is the same as y, which would lead us to conclude that y is equal to a half. Now, this has been done in a similar way to how we showed that x equals 1, although, unless you're Numberphile, this does seem a lot more questionable. To sort this out, we need to know the difference between convergence and divergence. First off, convergence, and here we're going to call the nth partial sum of 0.9 recurring what happens when you add up the first n terms, which here is 0 point and then n digit 9s. What this means is the nth partial sum is equivalent to 1 minus 10 to the minus n. So for any epsilon greater than 0, a partial sum gets within epsilon distance from 1, because there's always a big enough n for a small enough 10 to the minus n, such that the partial sum is a distance from 1 less than epsilon, and every subsequent partial sum is also a distance smaller than epsilon from the number 1. And doesn't matter how small epsilon gets, as long as it's above 0, this holds. From that, we know that the series converges to 1, and so 0.9 recurring is 1. But the partial sums behave differently on our second infinite sum. They are 1 for all the odd ends and 0 for all the even ends, but we keep jumping between 1 and 0, so the range never gets smaller and we never hone in on a single limit, which means we just simply cannot evaluate this sum. So in summary, x is defined and y is not. So the 2 points I'm trying to get across with this video are that every decimal expansion describes one number, and one number can be described by 2 decimal expansions sometimes. It's not just your calculator rounding up, and it's not just people trying to make maths a bit easier. It is a fact that some numbers have 2 decimal expansions. Now, I'm not going to prove my points here, but I am going to try and convince you. So for example, look at pi and its partial sums. 3, 3.1, 3.14, 3.141, and so on. They all tell us a bit about pi, specifically what it's definitely less than or equal to. So 3 tells us that pi is less than or equal to 4, 3.1 tells us that pi is less than or equal to 3.2, and I'm saying this because we know that these are the partial sums of pi, these are their digits before the dot dot dot. Going down, we get more and more precision as to a number which pi is definitely less than or equal to. I say or equal to because we could at some point be hit with a 9 recurring, and then it is just equal to the previous upper bound. This doesn't apply to pi because it's irrational, but I still want to keep it in for clarity. Now every time we add on a digit, the running total goes up a bit, but we also have these numbers which we know the decimal expansion cannot exceed. And there's a theorem called the monotone convergence theorem, which states that if a sequence is increasing and bounded above, it must converge, which means that every single decimal expansion converges, because they all work the same as the one in this example. Now I've demonstrated to you my second point, and it applies to any decimal expansion that ends in 9 recurring or just ends, which if you think about it is the same as ending with 0 recurring. And I think these two statements illustrate quite well why algebraic manipulation, as seen at the beginning of this video, is a-okay, because a decimal expansion cannot be manipulated and then broken by some weird tomfoolery. And now that we're all confident with algebraic manipulation, why not have some fun with it? So this example is what we did with 0.9 recurring, only it's a little more girthy, because instead we have x equal to 0.142857 recurring. What this means is a million x is 142,857.142857 recurring. Then if we subtract x from that, the recurring bits vanish, and we just have 999,999x equal to 142,857. Funnily enough, that means that x is 142,857 divided by 999,999, which is 1/7. So one thing I noticed while playing around with algebraic manipulation is that every rational number can be written with an integer part and then the finite decimal part and then the repeating decimal part. n.a be recurring is just how I sort of shorthanded that. And one open-ended question which I was thinking about is, can the denominator of a fraction in its simplest form tell us anything about the digit lengths of a and b, or do we also need the numerator to figure that out? I might do some research and show you my findings one day, but in the meantime here is a bonus clip of me doing algebraic manipulation on a Dosonal expansion to show you that the Dosonal expansion of 1/5 is 0.2497 recurring. If you don't know what the Dosonal system is, it's like the decimal system but with 12 instead of 10, and if you're still not sure what that means, then don't worry because my next video is going to be about that. Anyway, thanks for watching, make sure to smash like and subscribe for more videos like this and more memes. I'm going to leave you with me doing what I've been doing this whole video, only in binary this time because that's a pretty well known counting system.